Hi, my name is Ria, and this is Lab 3. So for this lab, we were given the mass and position of a star orbiting a black hole with an unknown mass, and we were asked to find the mass of this black hole. This is different from past labs because the gravity force is not that of the Earth, but the same physics concepts apply. So in this case, we can assume only a single force in that the black hole is the only force acting upon the star. We can therefore use Newton's law of universal gravitation, which is the net force is equal to the gravitational constant multiplied by the mass of the star, the mass of the black hole, and then divided by the position squared. We can also use Newton's second law, or the momentum principle, which is, in this case, that the change in momentum over the change in time is the same thing as F net. So just to walk through some of the code here, we have my GTID, or my Georgia Tech email, here as a seed, which allows us to randomize all of the position values for the star. Then here, the system properties, we have the gravitational constant, we have the mass of the star, we have delta T, which is 1 day in seconds. And then here's the actual loop where the data is being iterated. So we know that the initial momentum is just the initial velocity multiplied by the mass of the star. Similarly, the final momentum is the final velocity multiplied by the mass of the star. And then we know delta V and delta P are their respective final values subtracted by their respective initial values. So we know dp dt is delta P, which is the change in momentum over the change in time. And using Newton's second law, we know dp dt in this case is equal to F net because there is only one force acting upon the star. So in order to calculate dp dt parallel, we calculated p hat, the magnitude of dp dt, and then we multiplied those two to get the parallel component of dp dt. And that is also equal to the F net component, the parallel component of F net, because it's Newton's second law. We also know that dp dt parallel plus dp dt perpendicular are equal to dp dt. So in order to calculate the perpendicular component of the change of momentum, I subtracted the parallel component by the overall dp dt. So that allowed us to calculate the perpendicular and parallel components of F net. And then to find the actual mass of the black hole, which was the objective of this lab, I first calculated the magnitude of the star's position, which I called R, and then used Newton's universal law of gravitation to calculate the mass of the black hole, which is then printed, which we'll see in a second. And then while in the loop, in order to calculate an average of all of these sums, I just created an iterative adding function where it's just adding all of these, and then I then divided by the number of all the data points to calculate the average. So right down here we can see the average mass being calculated of the black hole, which is just a sum which was iteratively added in the loop divided by the length or the total number of values. And we can run this to see what it runs like. And here we can see all the mass values that are being calculated, and they're all fairly similar with a couple discrepancies due to the change in velocity. And so here we can see for F net, the value is 0.49. For F net parallel, we got 0.07. And then F net perpendicular, we got 0.484. And then the average mass of the black hole was 1.877 times 10 to the 34th, which makes sense in relation to the mass of the star, which was 2 multiplied by 10 to the 30th. So in conclusion, we know the net force and its parallel and perpendicular components are the same as the change in momentum and its parallel and perpendicular components, and that's Newton's second law. And this is, as our lecturers referred to it as, is the secret of the universe. And we also know it's possible to find the value of the mass of a new black hole given new position and velocity data, going through the exact same process that we had before, just changing the data. Thank you.